Okay, welcome back to Love and the Physics with Mr. Goldthorpe. We move on to vertical circles now. And I want you guys to imagine that we have an object swung in a vertical circle, so a vertical circle, not a horizontal circle. And it's done using what we call a massless rod. So I want you to imagine, you don't have to draw this, but imagine that there is some kind of massless rod kind of attached to that ball. And this thing is going around in uniform circular motion in some way. And that's what we're trying to analyze. But because the rod is massless, we can kind of ignore it. Okay, so let's ignore it. Let's get rid of it. All right, now the good news for you guys is you only have to analyze this motion in two different locations. One at the bottom of the circle and two at the top of the circle. So let's start at the bottom of the circle. So at the bottom here, again, if we draw the velocity and the acceleration, the velocity goes along the tangent. So there's the velocity vector. And remember, acceleration goes towards the center. I'll put that on the side. There's your AC going towards the center. Please make sure you draw those on your diagram as well, but as dotted arrows. Then we draw the forces. And now we can see that we definitely have the force of gravity acting on this. There's our Fg equal to mg. But there will also be a force coming from the rod itself. That will be a tension force. Can you see what direction the tension would have to go? And you'll see that because the acceleration is going upward, we better have an upward force here. In fact, a very large one. Here's your upward force called Ft. So there's our force diagram down here at the bottom of the circle. And if we establish a reference system, remember we always choose the direction of the acceleration as your positive direction. So down here, this would be your positive direction going upward. And then we can analyze this the way we typically do. So we know again that this is going to be uniform circular motion, or Newton's second law. And therefore we have F net equal to ma. But F net, you can see that Ft is going to be positive, Fg is going to be negative, equal to mac. Now we're going to stop here for a second because I want to show you something. This thing called mac, don't forget, this is also called Fc. And that means that's the centripetal force. So strangely enough, the centripetal force is not just one force, it's a combination of these two forces here, Ft minus Fg. And you know what? The way you can look at it is this. If you look at the force diagram, can you see that Ft is definitely going towards the center of the circle? So it is definitely trying to cause circular motion. That's why Ft comes out to be positive here. But can you see that Fg is going away from the center? It's resisting circular motion. Therefore, it's negative. That's why it's Ft minus Fg. Ft because it's helping the circular motion, and negative Fg because it's hurting the circular motion. Good. So now that is how you identify the centripetal force. And if you get Ft by itself, we discover that Ft becomes equal to mac plus Fg. It's the sum of those two. And what you have to know about this one is that when it's at the bottom of the circle, because of the sum of these two together, it turns out that Ft is going to be really large here. Or when you look at the force diagram, you'll see that because acceleration goes upward, Ft has to be bigger than Fg. And it turns out at the bottom of the circle, this is where you have maximum tension. It's really important you understand at the very bottom of the circle, it's where you have maximum tension. That's where the string or rod is most likely to break. Good? So that's the bottom of the circle. That's how we analyze it. Okay, let's now go to the top of the circle. So I'm just going to take a picture of, I'm just going to copy this and kind of transfer it down. So I can focus on the bottom here. Okay, now let's focus on the top of the circle. And again, we want to draw a force diagram. We'll start with the velocity and the acceleration. Velocity on the tangent, acceleration towards the center, and now the forces. We're still going to have a force of gravity acting downward. There's your Fg equal to mg. And now tension, remember tension acts towards the center. So therefore, the tension goes towards the center. And for this one, you see the acceleration is going downward. So therefore, this one should have a different reference system. We should have down is positive for this one. Good. Now, let's analyze it. So again, we use F net as ma. And F net now will be Ft, which is positive, and Fg, which is positive, equal to MAC. Once again, this thing called MAC is otherwise known as FC. So now your centripetal force is the sum of these two forces. Does that make sense? Remember, this is the force to try to cause it to go into a circle. Can you see that Ft is going towards the center? That means it's helping. And Fg is also going towards the center. So it's also helping. That's why they're both positive. So it's the sum of those two as a centripetal force. And if you get Ft by itself, you'll discover it becomes equal to MAC minus Fg. It's a subtraction of the two, which means it's going to be small. And specifically, this is where you have minimum tension at the top of the circle. And the logic behind this one is because Fg is already providing some centripetal acceleration, Ft doesn't have to be that big to complete it, to get as much as needed to get that centripetal acceleration. Sorry, that didn't come out very well. But because Fg is helping, Ft does not have to be big to create the same centripetal acceleration. That's why it's smaller. Okay, so there you go. This is kind of your responsibility. You have to be able to draw a force diagram for either the top or the bottom. You have to know that the bottom is maximum tension, the top is minimum tension, but then you just analyze it the way you ordinarily do for acceleration using second law. So here's an example. And my recommendation is you guys actually try this question yourself first. Just pause, give it a try, and then we'll go over this one together. Okay, now the first thing we're going to do is we're going to recognize that this is a minimum tension question. We're going to draw a force diagram. So you draw your best circle. We put the object down here. The key thing is this is at minimum tension. Sorry, I'm going to have to actually shift this down just a little bit. That'd be better. Okay. So we'll put that up. Now I have to realize that minimum tension, it has to be at the top of the circle. Okay, that's where you have minimum tension. So I'll just put that over here. This is at the top of the circle. You get 1 mark just for identifying that. Now we don't know which way this thing is actually going, so I'm just going to make it different. Let's go in a kind of a clockwise direction. Let's draw the velocities first. The velocity is on the tangent. Acceleration towards the center. And then the forces, as we'd already talked about, we have our Fg equal to mg. And we also have the tension force going towards the center. And we know the tension force. The minimum tension is 20 newtons, so this is going to be 20 newtons. And remember, since everything's going down, it just makes sense to choose down as positive in this question here. Good. And as we did before, we can now analyze this thing using uniform circular motion, second law, accelerated motion, whatever one you want. And this is going to be F net equal to MA. F net is the sum of those two, so it's going to be Ft plus Fg equal to MAC. And it turns out we actually know enough to find AC. We can see that AC will be equal to Ft plus Fg divided by the mass, or Ft plus Mg divided by the mass. So I don't know where my T went there. Okay, so that means we're going to have 20 plus the mass of this thing, which is 2.8 times 9.81 all over 2.8. Okay, let's find that first. All right, it's about 16.953 meters per second squared. Now our job after this is to figure out the length of the rod. And if we put that on the diagram, the rod would look like this. Whoa, except for the bulge there. Okay, anyways. But this is the rod that we're actually talking about. And you'll notice that the length of that rod actually represents the radius of the circle. Let's shade that in so it doesn't look so bad. Okay, there we go. Okay, so, and there's the ball right there. Okay, so the length here will actually represent the radius. So we're actually just solving for radius here. Good. So to do so, you'll notice also we're given the period of 0.72 seconds. So that means we need a formula with AC and period. So there's your AC equal to 4 pi squared r over t squared. We just want to solve for r. So we have AC times t squared when you cross multiply is 4 pi squared r. And then we get r by itself. So r becomes equal to AC big T squared over 4 pi squared. So we have 16.953. The period, we're told, is 0.72. So 0.72, don't forget to square that, over the 4 pi squared. Just a reminder, make sure that's in brackets when you put that in your calculator, if you do it all at once. Oh, yeah, that didn't come out well. Okay. So times 0.72 squared divided by 4 pi squared. All right, and sig digs for this one looks like 2. So I get about 0.22 meters. Okay, so now we know how to deal with vertical circles that involve like strings or massless rods, things like that. So I recommend you go try doing some of those questions first before you move on to the next section. I'll see you then.